Hello everyone and welcome to the Natural Language Processing with NLTK course. My name is Marion Kipsang and I will be your instructor today. On our agenda, we have learning outcomes. What is it that you're expected to have learned by the end of this course? We have what and why. What is NLTK and what do we use it for and why do we use it? So we have, after that, we have reading and quiz, where you will be able to read through a document that contains a bit more information on NLTK. And afterwards, you can take the quiz to gauge your understanding of the material. After the reading and quiz session, we will have the practice session. The practice session, we will be able to look at our workshop notebook and we will be able to see NLTK in action. And we will use it to implement text classification on a data set. So after that, we will have next steps, what to do after finishing this course. Now on to our learning outcomes. By the end of this course, you should be able to explain the importance and applications of natural language processing in various domains. For instance, in business, in the healthcare system, in banking, and in many other domains. You should also be able to understand the challenges that come with text preprocessing and the role of text preprocessing techniques like stopword removal, tokenization, stemming, and lemmatization. Apart from understanding the roles of these techniques, you will also be required to apply these techniques to preprocess a given text. After that, you will develop a simple text classifier that can be used for applications like sentiment analysis, after which you will evaluate the performance of your text classifier using appropriate evaluation metrics such as accuracy, F1 score, or recall. Now on to what is NLTK. NLTK stands for Natural Language Toolkit. It is a powerful and comprehensive library and it has been developed in Python and it has been designed to work with human language data, especially in the field of natural language processing. So we use it in a large number of real-world applications. Some of these applications include, we build applications that perform text classification and can be used for tasks such as social media monitoring and customer feedback analysis. We can also build applications that extract information from text. We can also build applications that perform machine translation. So these are applications that translate text from one language to another. For instance, Google Translate. We can also develop applications that understand and generate natural language, and these are used to implement chatbots and virtual assistants like ChatGPT. So now we will look at a real world example of natural language processing. So here we have Google Translate and we have given it this piece of text that is in Swahili. Habari yako leo ni siku njema. It has been able to detect that this language is Swahili and it has also been able to correctly translate this text into English as how are you? Today is a good day. Now let us look at why is NLTK important. First of all, it provides us with a comprehensive suite of text processing tools. So whatever text processing task that we can think of, NLTK provides tools for them. For instance, it provides tools for tokenization, for stemming, for parsing, for stopword removal, and for named entity recognition. It also has an extensive collection of corpora and lexical resources. When you talk about corpora, we are talking about large data sets, a large collection of text data that can be used for linguistic analysis. So NLTK provides us with a large set of data known as corpora, and this can be used to train and evaluate our models on diverse data sets, which improves their generalizability when exposed to real-world data. NLTK seamlessly integrates with other natural language processing libraries like Spacey. So this seamless integration allows us to combine its strengths with those of other libraries, thus enhancing the capabilities of our NLP projects. NLTK also supports a wide range of applications. We can use it to build a wide range of applications. For instance, applications for sentiment analysis, question answering systems, and many other applications that require natural language processing. Now, moving on to features of NLTK. NLTK comes with a wide variety of dataset, corpora, and lexical resources that are useful for research and development. Corpora is a large collection of text documents that can be used for linguistic analysis, while lexical resources, for instance, we have WordNet, which contains the set of synonyms for each word, including the set of synonyms. It's also its hyponyms and hypernyms, and also the antonyms of English words. It also provides a suite of text preprocessing modules that allow users to preprocess and analyze text. So whatever preprocessing and analysis task you would like to perform on your text data, NLTK will be able to provide for you tools that are easy to use for text processing. It also provides modules for machine learning. This enables the development of natural language processing applications that leverage the power of machine learning. It also supports various linguistic and semantic analysis tasks, such as syntax parsing, semantic role labeling, and co-reference resolution. By syntax parsing, we mean automatically understanding the syntactic relationships between words in a text. By semantic role labeling, we mean assigning categories to words depending on their semantic role in a text. And co-reference resolutions is finding all expressions that refer to the same entity in a text. So co-reference resolution is identifying all expressions that refer to the same entity in a text. Now, moving on to a comparative analysis of NLTK and other natural language processing libraries. So here we will compare NLTK to spaCy and TextBlob. In terms of scope, NLTK is quite comprehensive and it provides us with a wide array of tools. spaCy, on the other hand, is not necessarily known for its comprehensiveness. Rather, it is known for its speed and efficiency, making it suitable for large natural language processing applications. While on the other hand, TextBlob is designed to be simple and beginner-friendly, but this simplicity leads it to not be as comprehensive as NLTK. When it comes to use cases, NLTK is suitable for education purposes and research. spaCy has been specially designed for production use, and TextBlob is a good choice when creating quick prototypes and simple NLP applications. In terms of customization, NLTK is highly customizable. On the other hand, spaCy may not offer the same level of customization and extensibility that NLTK offers, and TextBlob may lack the advanced customization and flexibility of NLTK. In terms of speed and efficiency, some components in NLTK may be slower compared to spaCy for certain tasks. For instance, for named entity recognition, spaCy performs better and is actually faster than NLTK. So spaCy is fast and efficient, and it is suitable for large-scale applications. TextBlob is built on top of NLTK, so the same components that are slow within NLTK will also be slow within TextBlob. Now, on to related tools. These are tools that are used alongside NLTK. We have Python as the primary programming language. When we want to implement software solutions that make use of NLTK, we'll mostly use Python. Jupyter notebooks are used for collaborative development. They allow different users to access the same code base and work together collaboratively. So scikit-learn gives us access to machine learning models that we can use for text classification or document clustering. Pandas help us. It helps us work with structured data using data frames, and regular expressions are used when chunking or parsing. So that is when extracting verb phrases or noun phrases from a text. Now, moving on to important NLTK concepts. Some of these concepts include corpus. As we had said earlier, corpus is a large collection of text documents that can be used for linguistic analysis, and NLTK provides us with a wide variety of corpus. For instance, we have the movie reviews dataset, we have the Reuters dataset, we have the Brown dataset, so many different corpus that we can use for training and evaluating our machine learning models, or even for analysis and learning. There's also tokenization. Tokenization is the process of breaking down text into individual units called tokens. These tokens can either be words or sentences. And stopwords, these are words that are commonly used in language but do not necessarily carry much meaning. So during analysis, stopwords are usually removed, and removing them improves the results of our analysis. We also have part of speech tagging. This is assigning grammatical categories to words, for instance, nouns, verbs, and determiners, among many other parts of speech. Stemming and lemmatization involves breaking down text, breaking down words into their base or their root form. Stemming does it by removing affixes, so prefixes and suffixes, and the resulting word may not necessarily be a valid word. On the other hand, lemmatization considers the contexts in which the word is used, so it reduces words to their dictionary form. So the results of lemmatization are always valid words. Then named entity recognition. So this involves identifying named entities within a text. So some named entities include persons, organizations, money, dates, and times. We can also perform chunking. This involves extracting word phrases, extracting noun phrases or verb phrases from a piece of text. And then we can also perform machine learning in NLP, in natural language processing, and we also have access to linguistic features and resources from NLTK. Now on to our reading and quiz section. So here you can pause the video, take 10 minutes to look at the reading document, and also try out the quiz to gauge your understanding of these materials. Now onto the practice session. Here there's a link provided in the video description. This link is linked towards, it's a link to the Python notebook that contains the Python notebook that we will use for this section. So once you've opened your notebook, go to File, save a copy in Drive, and then after saving a copy in Drive, you connect it over here. So this is so that you can run the code and even make changes to the code. So you go to File, save a copy in Drive, and connect. So if you have successfully connected it to a runtime, you will see a green check mark. So NLTK is the go-to library for working with human language data. We will start by importing the necessary libraries that we will need in this notebook. So we will first import NLTK, which will provide us with the tools for natural language processing tasks. We will also import pandas. This will help us work with structured data in structures known as data frames. And we'll also install scikit-learn. Scikit-learn will provide us with tools for machine learning. So we'll just run this cell to ensure everything has been imported correctly. and then loading data. So in this notebook, we will use the movie reviews dataset, and I have provided a shortened link to the dataset. So this dataset contains the reviews of movies and labels indicating whether the review is a positive one or whether it's a negative one. So we use pandas to read the data into a data frame, and we can preview some of the data. We can preview the first 5 rows of the data and see how our data looks like. So as you can see, we have these columns, text and tag. So our column of interest, the column that contains the actual reviews, is the text column, and this is the column we will focus on while performing text pre-processing and analysis tasks. So we will move on and pre-process our texts. Now, text pre-processing, these are tasks and techniques applied to raw text before using it for analysis or modeling. So we will pre-process the text column of our dataset because that is our column of interest. So we will start by performing tokenization. As we had said earlier, tokenization is the process of breaking down text into individual units, and these units are known as tokens. Tokenization is a crucial step in preparing text data for analysis. And in NLTK, we can perform 2 kinds of tokenization. We can perform word tokenization, which is breaking down text into individual words, and we can also perform sentence tokenization, which is splitting text into individual sentences. So we will start by performing word tokenization. First of all, we have to import the word tokenization function from NLTK, and this function is called word_tokenize. Other than that, we have to download this pre-trained model called Punkt, which also assists in tokenization. Then we will create a new column known as word_tokens, and in this column we will apply tokenization to the text column. So we can preview our data to see what has happened, how tokenization has been performed on our column. Now, as we can see, we have our text column. It has films. Let's look at the first entry in our text column. Films adapted from comic books have had plenty, and so on and so forth. And then we will look at our new column called word_tokens. And as you can see, we have a list. We have a list of all the words that were in the sentence from the first column of our text, the first entry in our text column. So we have a list that contains films adapted from comic books, and so on and so forth. We can also apply sentence tokenization to our column to see what happens. We perform sentence tokenization similar to word tokenization. The only difference is that we use a different function. So the function for sentence tokenization is called sent_tokenize, and we can run this and see what happens. So as you can see, this one, the sentence tokens column, it is also a column that contains lists. So it contains a list of sentences, while the word_tokens column contained a list of words. The sentence_tokens column contains a list of sentences. Moving on to stopword removal. As we had said earlier, this is the process of eliminating common words that are considered to be of little value in terms of conveying meaningful information. These words, they're known as stop words. They include articles, prepositions, conjunctions. So they are high-frequency words that are necessary for the structure of a language, but they do not contribute much when analyzing text. So the way we perform stopword removal is we first import the stopwords corpus from the NLTK library. And then we download the stopwords corpus, after which we create a set of stopwords. We name it stopwords, and this is a set of stopwords.words, and we specify that the stopwords we want are the stopwords from the English language. So we then create a function to remove stopwords from a list of tokens. We call this function remove underscore stopwords, and this function takes in a list of tokens. So here we return a token. We iterate through the tokens and we return the tokens that are not in our stopwords. So this is what this section of the code means. We iterate through the list of tokens, and if a token is not in stopwords, we return it. So at the end, we have a list that only contains words that are not stopwords. So we apply this function to the word underscore tokens column of our data frame by creating a new column known as filtered tokens. And then we will take a look at how this column looks like. So as we can see, for instance, when we go back to our word tokens, let us look at the second entry in our word tokens column. So we have 4 starters. It was created by Alan. And when we look at the second entry in our filtered tokens column, we have starters. So 4 has been removed. It has been removed. Was has been removed. We have created. We have Alan. So we have 4 has been removed. It and was. All those are stopwords and they have been removed. Now onto stemming and lemmatization. Stemming is a technique that involves reducing words to their base or root form, and this form is known as a stem. The goal is to group words with similar meanings, even if they have different inflections or derivation. So this is how stemming works. Stemming takes a word and removes any prefixes or suffixes from the word to get a root form of the word. So it may not always produce valid words because its goal is to normalize our data set rather than to maintain semantic accuracy. So some algorithms that we can use for stemming, we have Porter stemmer and Lancaster stemmer, and they're implemented in the same way. So first of all, to implement stemming, we will import the Porter stemmer algorithm from NLTK. We will then create an instance of the stemmer class. After creating an instance of the stemmer class, we create a function that will perform stemming. So in this function called apply stemming, this function, it takes tokens and applies stemming to these tokens, and this is how it works. First of all, we initialize an empty list, and then we iterate through the list of tokens. So for each token in the list of tokens, we stem it by saying stemmed token is equal to PS, which is the instance of the stemmer class, dot stem, and into bracket token. And then we take this stemmed token, we take the stem of this word and append it to our list of stemmed tokens, and we return this list. So we can apply this function we can apply it to the column of filtered tokens to see what we get, and we call this filtered underscore tokens underscore stemmed. So as you can see, we can take a look at in our word tokens column, the first entry has films adapted from comic books have had, while in our filtered underscore tokens underscore stemmed column, we have film, adapt, comic, book, plenty. See, this plenty is not a valid English word, so the stem of plenty is not a valid English word. Then success. So you can see it reduces words to a base or root form that may not necessarily be an English word. On the other hand, lemmatization reduces words to their base or root form known as a lemma, also known as the dictionary form of a word. So the goal of lemmatization is similar to stemming, but it produces valid words, and it considers the context and meaning of words. So to implement lemmatization, we have to import the lemmatization algorithm known as WordNet Lemmatizer. Then after importing this algorithm, we will download the WordNet corpus. And then we create an instance of the lemmatizer class, and similar to the stemming function above, we write a function that applies lemmatization to our list of tokens. So we do this by initializing an empty list and then iterating through the list of tokens. So iterating through this list of tokens, we lemmatize each token in each word, we lemmatize each word, and then append the lemma to our list of lemmatized tokens. Then we can do the same thing. We can lemmatize the entire filtered underscore tokens column by applying our function, and let us see what our results will be. So as we can see, we can compare the lemmatized tokens to the filtered tokens. We have film, adapted, comic book, plenty, success. So every word here is a valid English word. We have reduced the words in the sentence. As you can see, adapted remains adapted because in the sentence, adapted being in the past tense makes sense in the context of the sentence, so it remains adapted. And like when stemming, adapted was reduced to adapt. So now we have a challenge. I have provided you with a dataset known as the rooters dataset. This rooters dataset is a collection of documents that have labels. They have labels like crude, moneyfx, and many other labels. So what you are required to do in this challenge is you have to apply tokenization to the text column. So as you can see, we have the categories column and the text column. So our text column is our column of interest, and our categories column is our column of outcomes. So what you're required to do is apply word tokenization on the text column, and then you're also required, after performing word tokenization on your list of words, remove all stop words from that list of words and create a new column that contains a list of words that do not have any stop words in them. So that is a challenge for you. You can pause the video, take a few minutes to see whether you can implement that. Next, we will move on to analyzing the structure of our dataset. So what we can do is perform part of speech tagging. Part of speech tagging is the process of assigning grammatical categories to each word based on its syntactic function within a sentence. So this involves identifying nouns, verbs, and many other parts of speech. So there's a website I've provided here which shows us the different parts of speech that we have, that you can get when using NLTK to tag parts of speech. So let's see how we implement part of speech tagging. First of all, we import the part of speech tagging function from NLTK, which is POS_tag. We also download the average perceptron tagger. This is a model that performs part of speech tagging. Then we create a function to perform part of speech tagging. So this function is called apply_POS_tagging, and it takes in a list of tokens. And after taking it at a list of tokens, it returns a list that contains tuples, and this list contains tuples that contain the word and its part of speech tag. So we can apply these functions to our function to perform part of speech tagging to our list of tokens. And then we create a new column called POS underscore tags, and we can preview the data set and see what it does. So this function will take a while to run because our data set is fairly large. So we can see our output here. We can look at our POS underscore tags column. The first entry has films, and films has been given the tag NNS. We can go to our website to check what NNS is. And as you can see, NNS is a noun that is in its plural form. So films is a noun and it is in its plural form. Adapted is a VBD. VBD stands for verb past tense. So adapted is a verb that is in past tense. From is an IN. We check what IN is. IN is a preposition or a subordinating conjunction, and so on and so forth. So as we can see, we have been able to assign parts of speech to our tokens. Next, we can do named entity recognition. This is a task that involves identifying and classifying named entities such as persons, organization, dates, times, money, among any other entities that can be identified within a text. So its goal is information extraction and categorizing specific pieces of information from unstructured data. So to perform named entity recognition, we first import our function that performs named entity recognition, which is NE underscore chunk. And then we download these two resources, Maxent underscore NE underscore chunker and words. After that, we create a function to perform named entity recognition. We name the function named entity recognition, and this function takes in tokens. So what it does, it creates this variable known as named entities, and these named entities are the named entities that it finds within our list of tokens. So NE underscore chunk, give it tokens, it will produce for you a list of named entities, and then we return these named entities. We can create a new column that has our results of named entity recognition, and we can create this by applying our function to the column that has words alongside their parts of speech, yeah. So we can run this and see what it gives us. This one will also take a while because our data set is fairly large. So you can pause the video as you wait for it to run. Now we can look at what we have here. Again, the results are not very clear. Maybe you can use a smaller piece of text and apply named entity recognition to a smaller piece of text. Moving on, we have WordNet. WordNet is a lexical database of English language that is organized into a set of synonyms, and this set of synonyms is called synsets. And it also provides relationships between these synsets. So the key features of WordNet include synsets, which are sets of synonyms, words that can be used interchangeably without really changing the meaning of a text. Hypernyms are a hierarchical. Hypernyms and hyponyms provide a hierarchical organization of words, since a hypernym is a more general or abstract term, and a hyponym is a more specific term. For instance, in the hierarchy, animal is a hypernym of cat, and cat is a hyponym of animal. The other feature of WordNet is antonyms. Antonyms include information about words that have opposite meanings. So we will start by looking at synonyms. Synonyms are words that have similar meaning. They can be used interchangeably in certain contexts without changing the overall meaning of a sentence. So the primary goal and purpose of synonyms are: it helps improving the understanding of a word by providing alternative words that convey similar meaning. It also is very helpful in information retrieval and search applications. So the synonyms can be utilized to expand search queries and ensure that relevant documents containing synonymous terms are also retrieved. And they allow for more robust and nuanced analysis of text by considering different ways of expressing the same idea. Now, how do we get, given a word, how do we get its synonyms? First of all, we import WordNet and we create an empty list of synonyms. Then we iterate over all the synsets of the word good. After iterating over all the synsets of the word good, we iterate over all the lemmas in syn.lemmas, and we append the lemma of the name to our list of synonyms. So we can run this and see the set of synonyms for the word good. As we can see, good is synonymous to adept, skillful, well, safe, secure, and decomposed, estimable, honest. So there's so many synonyms for the word good. Moving on to hyponyms. Hyponyms are words that represent a more specific concept or category within a broader category. So in other words, a hyponym is a type of a more general word, which is a hypernym. So they help create structured and hierarchical representations of the English language semantic space, and it is valuable in natural language processing tasks like semantic analysis and information retrieval. So how exactly do we get the synonyms for a word? We start by initialize the hyponyms of a word. We start by initializing an empty list of hyponyms, and then we iterate through the synsets for our word good. And then after iterating over the synset, we iterate over the hyponyms within each synset using the syn.hyponyms method. And then we append the name of the hyponym to our list of hyponyms. So we can run this and see what our results will be. As we can see, some hyponyms of good are virtue, desirability, middling, wisdom, worldly possession, and many more. Moving on to antonyms. Antonyms are words that have opposite meaning, and they're often used to express contrast or opposition. So there's the inclusion of antonyms in WordNet serves several purposes. For instance, recognizing antonyms is crucial for understanding the nuances and contrast in meanings between different words. This information is valuable in NLP applications like sentiment analysis, question answering systems, and machine translation. It enables the natural language processing systems to better capture the intricacies of meaning, which is essential for tasks like information retrieval, summarizing text. And then they also provide a clear contrast to synonyms and indicate the opposite ends of the semantic spectrum. We can run, so how do we get the antonyms of a word? First of all, we initialize an empty list and we iterate over all its synsets. So after iterating over all its synsets, we iterate over all its lemmas, and if we check if the lemma has an antonym. If the lemma has an antonym, we apply the first antonym in the list of antonyms to our list of antonyms. So we can run this and see the outcome, and we can see that the antonyms for good are bad, ill, badness, evilness, and evil. So there's a challenge for you to do right here. This challenge requires you to use WordNet and find the synonyms, hyponyms, and antonyms for the words bad. You can pause the video, see whether you can do it, and then we'll continue. Now we can move on to text classification. So text classification is a task where we use machine learning algorithm to categorize text into predefined classes or categories. So the first step here is to split the data into a training and testing set. So to split the data, we have to import the train test split function from scikit-learn. And after that, we can split our data into our set of training features, our set of testing features, our set of training labels, and our set of testing labels. And we just use the train test split. We specify our set of features, which is the movie reviews text column. We specify our set of labels, which is the movie reviews tag column. We set our test size to 0.2, meaning that 20% of our data will be used for testing and 80% for training. Then we set random state to 42 so that we have consistent results every time we run the code. So we can run this. Now that we have our set of features, they're not in a suitable state for use with machine learning models. We have to convert them to some numerical form. This is where vectorization comes in. So here we will perform term frequency inverse document frequency vectorization. So to make sure that we have a numerical representation for our text. So that the machine learning models are able to work with our text. So a brief explanation of how TF-IDF vectorization works is that we find the term frequency. This measures the frequency of a word within a document, and then we find the inverse document frequency. This is the importance of a word across a collection of documents. Then the TF-IDF score of a word in a document is obtained by multiplying its term frequency by its inverse document frequency. Then, therefore, each document in the corpus is represented as a vector of term frequency inverse document frequency scores for each term. And the resulting vectors can be used for various natural language processing tasks such as document clustering, text classification, and information retrieval. So how exactly do we perform TF-IDF vectorization? First of all, we import TF-IDF vectorizer from sklearn, and then we create an instance of the TF-IDF vectorizer class, and we specify the maximum amount of features we want in our data set. And then we use fit transform and transform to vectorize our set of training and testing features. So we'll run this. After that, we are ready to perform any modeling. We're ready to use our machine learning models. So we will start with a multinomial naive Bayes model. Multinomial naive Bayes model. So what we'll do first is we will import our multinomial naive Bayes algorithm, and then we will create an instance of the algorithm, which is creating our model. We will name our model M and B classifier. So after creating our model, we will train it on our set. We will give it our set of training features and our set of training labels so that it can learn the relationships between the training features and the training labels. After training, we will make predictions using our trained model. So we do that by taking our model M and B classifier.predict, and we give it our set of testing features. And then we can evaluate our model's accuracy, our model's performance by displaying the accuracy, calculating the accuracy, calculating the confusion matrix, and printing out a classification report. So as you can see, our model has an accuracy of 0.669, roughly 0.67. So it means it has correctly classified 67% of instances in our test data set. So, and we also have our confusion matrix, the elements in the diagonal of the confusion matrix. So 4,156 and 4,513 represent it represents the text that has been correctly classified, while 2060, 2215 represents instances that have been incorrectly classified. So our classification report shows us the precision, recall, and F1 score and support for each of our outcomes. So for negative, we have a precision of 0.67, a recall of 0.65, and an F1 score of 0.66. For positive, we have a precision of 0.67, 0.69, and 0.68. And then we have 6,371 negative instances and 6,576 positive instances. So our model hasn't performed so badly, but it can do better. We can do better by tuning hyperparameters, but that is beyond the scope of this course for now. Now, moving on to another model, we can train a Gaussian naive Bayes and see its performance. So first of all, we import our model. We import our algorithm and create our model. We name it GNB classifier, and then we train it on our set of training features and our set of training labels. After training it, we use it to make predictions. And after that, we can evaluate its performance. So this one has performed, its accuracy is 0.647, 0.65, meaning it has correctly classified 65% of instances, but it has performed slightly worse than the multinomial naive Bayes. Now onto the challenge. Using the dataset that I had provided in the first challenge, the Reuters dataset, you're required to train a Bernoulli naive Bayes classifier and calculate its accuracy and determine whether it is performing well or it isn't performing as well as you would like. So, and that is it for the practice session. That is it for the practice session. Now you can go to the After Work platform where you will have access to a project where this project involves developing a model that can analyze the sentiment of a tweet. And you will find that we've also provided you with a guiding notebook for the project. Other than that, thank you for being here, and